Alright, in this video we're going to be taking a look at Cartesian coordinates. Now, given that you most likely have an interest in computer graphics or graphics related programming, I think it's safe to assume that most, if not all of you, have a very firm grasp on Cartesian coordinates. Therefore, this video is probably going to be redundant for you, and please feel free to skip on to the next video. However, before you do, I did quickly want to mention that the subject of whether a 3D coordinate system is left or right-handed is covered briefly towards the end of this video. And that's something that's less commonly known, but it's very useful to know. It's very useful to understand how the terms left-handed and right-handed apply to a 3D coordinate system. So you may wish to fast forward to that part of the video even if you skip everything else. So despite the fact that most viewers will have a very firm grasp on Cartesian coordinates, there's such a fundamental concept that drives how we think about 2D and three-dimensional space that this training DVD just simply wouldn't be complete if I didn't include at least a brief introduction to Cartesian coordinates. Certainly all 3D applications that I've ever encountered have represented 3D space in terms of Cartesian coordinates. Most computer programs in general, if they have a 2D or 3D space, they are representing that space under the hood using Cartesian coordinates. Thus, it's highly likely that a significant proportion of the problems that you're going to encounter and that you wish to apply maths to in order to solve those problems, it's highly likely that they're going to occur in Cartesian space. So what is this Cartesian space and what are Cartesian coordinates? Well, it's going to be easiest to explain if we think about 2D space first, since this whiteboard that I'm drawing on exists in 2D space. It is a 2D plane, if you will. And every single point on this whiteboard, we know that there are a huge number of points that we could put on this whiteboard. Every single point is distinct from any other point, and we know that because the position of this point in the 2D space is unique for each point. But how can we identify a point based on its position, based on its location in 2D space? Well, we need some kind of labeling system. We need to assign each point coordinates, some label that defines exactly where in 2D space that location exists. And that is exactly the problem that French mathematician René Descartes, who used the name Cartesius in Latin, faced in the early 1600s. Whilst he's not the first person to use coordinate systems by any means, ancient civilizations have been using coordinate systems for hundreds, if not thousands of years previous to this, he was the first person to publish scientific writings on the coordinate system that we frequently use today, and that's why it's named after him. That's why it's named Cartesian coordinates. So Descartes devised a system where a point on a surface, i.e. a point in 2D space, can be defined and specified by using two intersecting axes as measuring guides. Now that may sound a bit complicated to anyone who hasn't encountered Cartesian coordinates before, but it's actually a very simple idea. So I'm going to start out by drawing just a single axis, a single measuring guide, and I'm going to draw this horizontally on the whiteboard. So let me draw a horizontal line. And hopefully the measuring guide that I'm about to draw up is going to be very familiar to those of you who have studied mathematics in school. Certainly in Western society, I imagine that this is taught from quite a young age. It's a number line. So we've got a straight line, and we're going to mark a point on this line as being a value of 0. Then as we work in one direction along this line, we're going to count upwards from 0 at even increments along the line. So I'm going to put some even points on the line, and we're counting upwards, so 1, 2, 3, 4. And in the opposite direction, again in even increments, the same increment as we were going along in the right direction, we're going to count downwards, -1, -2, -3, and -4. So pretty basic, it's just a number line, but there's actually a lot more to this number line than is first apparent. So we had to decide on a number of things on this number line that we may not have even realized we were deciding. Perhaps the most important was we had to decide on an origin for this line, a point on the line where we start counting from. That's the point that we marked with a value of 0. So this 0 value, this is our origin. So we had to decide on an origin. We also had to decide on an orientation of the line. We could have had a line going this direction or a line going in this direction, but we decided that we wanted a horizontal line. We had to decide on that unit of measure, the spacing and increments of each of our units in both directions. And then we had to decide which direction is going to be positive and which direction is negative. In other words, the positive direction is the direction in which we count upwards, and the negative direction is the direction in which we count downwards from 0. So we actually had a number of decisions we had to make, and with those decisions we have defined this number line, and we can now, using this number line, represent any one-dimensional point. That is to say, we can represent any number, because a number has a single value, it's just a one-dimensional entity. So let's say we had the number 3, well, we know that that exists right here on our number line, right here in our 1D space. We had the value -2, that would be right here. If we had the value 0.5, it's going to be right here. So you can see, using our number line, we can represent any point in 1D space. But we can extend this concept further than 1D space. We can extend this idea to 2 dimensions if we introduce a second axis, a second number line. Now, there are far less decisions that we can make with this number line than when we created our first one. So before, we had to decide on an origin. We decided that this point right here is our origin. But with our second line, we must share the same origin as the first. So that means that our line is going to pass through this point. So we might have a line like so, or another line like so, but it's going to pass through the origin. We also had to decide on an orientation for our first line. But with our second line, we must be perpendicular, that is at a 90 degrees angle, or also known as a right angle, to our first line. So that means we already can draw our line in. I'm going to erase the word origin, and because our line's coming straight down, I'm going to erase that 0 for a second. So we know our line must pass through this point, and it must be 90 degrees from horizontal, that is to say it's going to be vertical, so we can actually draw our line in. So it's going to come down like so. Way, that was a very long line. Let's try that again without Photoshop jumping like crazy. So I'm just going to go that far so Photoshop doesn't jump on me. And then let's draw this guy upwards. There we go. And now I'm going to put our origin back in as a 0. So we know that our line has to be perpendicular to our horizontal line. We can draw our line in now. We also must use the same unit of measure as our first axis. So that means I can put our marks along here with the same spacing, and we know we're going to be changing in increments of 1 between each of these spacings. So the only real decision we have to make is whether we count upwards going up the number line, or upwards when we go down the number line. Now, by convention, we simply, if we were to have these two axes on the page, when we go right or upwards, so basically as we're going upwards or to the right, we're going to count upwards, whereas if we're going left or down, so downwards or to the left, we're going to count downwards. That's just convention. So that means as we go up, we're going to be counting up. As we go down, we're going to be counting down. So that's convention. Another convention is actually how these two lines, how these two axes are named. The horizontal line is commonly referred to as the x-axis, and the vertical line is commonly referred to as the y-axis. So if you hear people talking about x-axis and y-axis, that's basically what they mean. They're talking about these two lines right here. So whereas before a point along the 1D number line simply consisted of a single number, for example, this point right here would be 1.5, because it exists halfway between 1 and 2. So a 1D number line point consists of a single number. A point in 2D space is going to be represented by a pair of numbers. It's going to be represented by its coordinates. And its coordinates are going to look something like this. We're going to have two numbers in parentheses separated by a comma. The first number is going to tell us something about x. The second number is going to tell us something about y. And it really is very simple. The x number tells us how far along from the origin do we travel along the x-axis? So that's what this guy means. And our y number, our y coordinate, as I start to introduce the word coordinate there, our y coordinate tells us how far from the x-axis do we travel in the y direction, so perpendicular to the y-axis, to get to our point. So if we had a point right here, we can see we need to travel along our x-axis 3 units, since he is sat right there at 3 units in x, and then we need to travel up in the same direction as y 2 units. That means this point has an x coordinate of 3 because we travel 3 in x, and a y coordinate of 2. If we were to take another example, maybe this guy right out here, we travel in the x-axis -3. So that gives him -3 in x, and we can see we then have to travel up parallel to the y-axis by 1 unit. And let's take one final example. I don't know. Let's take this guy right here. So one final example, we have to travel along in the x-axis by -4 units. And then we travel down parallel to the y-axis by -3. So that gives us -4, -3. So it's really easy. These are the coordinates of that 2D point, and we have an x-coordinate and a y-coordinate, and they tell us explicitly where in 2D space that point exists. And it really is that simple. The real power of Cartesian space, this is a 2D Cartesian space defined by an x and y axis, the real power of that space is that we can take an equation that relates 2 or more variables, for example, something that said, I don't know, y equals x plus 2, and we're going to see this a lot more in subsequent videos, but this is an equation that relates an x variable and a y variable, and we can actually graphically represent that in this space by saying that, well, this is a set of y coordinates for a set of x coordinates. If we have a set of x coordinates, we generate the corresponding set of y coordinates, we plot them in this Cartesian space. We're going to see this a lot more in the next few videos, so don't worry if this doesn't quite make sense right now. But it allows us to plot this in Cartesian space and to think about equations graphically. And really, that's essential. It's essential for the area of mathematics known as analytic geometry. It's essential to computer graphics and everything that we do. So everything that we do really is so reliant on Cartesian coordinates. Hopefully you can see just how important they are and why I felt it was essential that they be covered on a DVD such as this. So continuing on, we've seen 2D space. What about 3D space? So I'm going to scroll down. Well, let's say that we have 2D as being x and y. Well, to create 3D, we need a third axis, which by convention is called the z-axis, and that's going to be perpendicular to both our x and y axes. So if I was to draw, this is our y-axis, and imagine we're looking at a 2D plane, a 2D sheet of paper, if you will, that's standing up in 3D space. So imagine, I don't know, if this was a piece of paper, then you can see that we're not looking at a distorted x and y axis, we're looking at x and y in 3D space. We know they're at a right angle to each other. So here's our 2D space, but we can only define points that lie on this plane using these two axes. If we create a third axis, it needs to be perpendicular to both x and y, so something like this would work, because it's perpendicular to y, and it's perpendicular to x. That would allow us to, after we've defined how far do we travel in x up to a certain point, or rather along x to a certain point, then how far up in y to that point, we can now define, well, how far out in z do we travel to get to a point in 3D space. It lets us move points off of this plane into 3D space. So let's say, for example, I'm going to draw, so this is a little cleaner now that I've scribbled all over that diagram. This is x, y, z, and I don't know, 1, 2, 3, 1, 2, 3, and 1, 2, 3. So if I had a point, I'm just trying to work out where I want to put this guy, I don't know, something like this, And let's just say that this point actually lines up here on our xy plane. We can see, okay, we need to travel, let's say 1.5 units in x. We then need to travel up, I don't know, 2.5 units in y. And then we need to travel out from here in the z direction, which appears to be, it's a little hard because obviously it's a 3D drawing, but I'm going to just say about 2.5. This is a very rough example. 2.5 as I squeeze this in, and you can see that whereas before we had 2D coordinates with x, y, in 3D it's simply extended to x, y, and z. How far do we travel in the x-axis? How far do we travel in the direction of the y-axis from that point on the x-axis? And now in 3D space, how far do we travel from our point on the xy plane along the direction of the z-axis to move us out to our position in 3D? So that's how 3D space works. It's a very simple extension of the 2D idea. But notice when I drew our x-axis and y-axis, this is our y and this is our x, which are perpendicular, and I said our z-axis needs to be mutually perpendicular to both of these. It needs to be perpendicular to both the x and the y, and I just drew a line out here and said, yeah, this guy, he's perpendicular to both. We can see he's at a right angle to x and he's at a right angle to y. Fantastic. There's actually another direction that that line could have gone in. Our axis could have gone in this direction. Notice it's also perpendicular to y, it's also perpendicular to x. So which one of these is the correct z-axis? Well, actually, both of them can be the correct z-axis. This is exactly where the idea of a left-handed and a right-handed system comes in. So how do we know which is which, and how do we know which we wish to use? Well, a right-handed system can be determined by basically using your right hand. It's exactly where the phrase comes from. So if you were to hold your right hand out in front of you, and then extend your thumb so that you're giving the thumbs up sign and pointing your thumb up to the ceiling. Now extend your index finger so it's pointing away from you and level, horizontal, so pointing straight away from you. And finally, bring out your middle finger so that it is perpendicular to both your thumb and your index finger, so it should be pointing out to the left if you're using your right hand. This is a set of axes, if you will. It's a set of 3 different directions that are all perpendicular to each other. So feel free now to move your arm and your hand. Just keep your fingers perpendicular to each other. We can assign different axes to different fingers. So long as we assign them in the right order, we define a right-handed system. So we're defining x, y, and z. It's always referred to in that order as x, y, and z. So you're going to assign these in the order of thumb first, then index finger, then middle finger. So the thumb gets x, the index finger gets y, the middle finger gets z. So now we know that, okay, this is x, y, and z. Well, looking at our diagram here on the whiteboard, align your thumb with the x-axis, align your first finger, your index finger, with the y-axis. Notice which direction our middle finger is pointing in. That is the direction of z in a right-handed system. It should, unless you've got crazy double-jointed fingers, it should be pointed in this direction. So this is z in a right-handed system. But what if you were to hold up your left hand again, making your thumb, first finger, and index finger and middle finger all perpendicular to each other, and again assigning x to your thumb, y to your first finger, and z to your middle finger? Notice now, if you align your thumb with x and your first finger with y in our diagram, notice your middle finger points in the other direction. So your middle finger should be pointing in this direction, and that is going to be z in a left-handed system. So how do we choose? How do we know which is right? Well, the choice of whether to use a left or right-handed system is completely arbitrary, and different 3D applications might use different systems. Such choices don't really have a huge impact. I mean, when you get into looking at transformations and things, really all we've done is flipped everything, mirrored everything along the xy plane. So instead of it being positive in this direction, it's now positive in this direction. Don't worry if that didn't make any sense. If we eventually get to transformations, then you're going to see that hopefully this does make a bit more sense. But really it doesn't impact anything until you're dealing with representing transformations inside of a computer. So it's just an arbitrary decision. The only reason I wanted to bring it in at this point is so that you're aware that you can represent 3D space using either of these different handed systems, and that they can impact equations and things. So just be aware of it. And it's just something to be aware of, especially if you're looking at your 3D application. You notice, oh, this one's using a left-handed space, or this one's using a right-handed space. Now, my personal experience has been that almost every 3D application I've personally worked with uses a right-handed system. So unless otherwise noted, all the videos in this training series are going to use a right-handed system. All of the theories and the methods that we develop are going to be based on a right-handed system, and all of the diagrams that we draw that have 3D space are all going to use a right-handed system. So again, it's not something to concern yourself with. It's just something that's worth knowing. If you hear someone say, oh, I'm defining a right-handed 3D space, or oh, I'm defining a left-handed 3D space, now you know what they mean. You know how to determine the relationships between the three axes in that space, and you also know how to determine which of the two systems your particular 3D application is using. So this was a very brief introduction to Cartesian coordinates. There is a lot more information that I could have gone into, but that information is available very readily on the internet and in books, and I just wanted to have at least a brief introduction here on the DVD for those of you that haven't covered Cartesian coordinates before, or maybe have, but it's been such a long time that you've really forgotten how they work and you just wanted a refresher. Hopefully this video has served you guys very well, and hopefully you're very comfortable with Cartesian coordinates now, because it is such an essential topic for computer graphics and graphics related programming, and it lies at the core of almost every mathematical theory that's going to be covered throughout the rest of this DVD series. So it was kind of important to have a video that covered it. And with that, that is going to conclude this video. Thanks a lot for listening, everyone.